So this is the first of 3 lessons in which we look at solving quadratic equations. We're going to look at 3 different methods of solving quadratic equations, and one of them specifically in this lesson. The other 2 we'll save for other lessons. Now, before we take a look at solving a quadratic, we want to make sure that we fully understand what a quadratic is. So what I've got here is the standard form of a quadratic that you're probably used to seeing from previous math classes. So you've got y equals ax squared plus bx plus c. An example of that might be y equals 3x squared minus 4x plus 2. Now the key piece that makes this a quadratic is the fact that it has an x squared term in it. Right? If we didn't have this x squared term and all we had was y equals bx plus c, or as the example goes, y equals negative 4x plus 2, that's back to a linear equation. So the piece that makes this exponential, or rather, I'm sorry, quadratic, is the fact that it has this ax squared piece, and then in this example, the 3x squared piece. So we know something is a quadratic if it has an x squared in it, and that's the largest exponent value. So an x squared is what we're dealing with, which actually makes it a little interesting to try to solve for. Now another form that we're going to have to get used to of a quadratic is what is called vertex form. Vertex form over here looks like y equals a times x minus h squared plus k. An example of that might look like y equals 5 times x plus 2 squared plus 5. Now what I want you to notice is that I still have an x squared. An x squared in this example down here, we still see that. Yes, the x has something added or subtracted to it in maybe a different example, but the term that has the x in it is still squared, so this is still a quadratic. It is still a quadratic. So this is just a different form that you may need to get used to. If you ever see anything that has an x squared in any of these forms, you know that it is a quadratic equation. And there's going to be several different methods that we're going to look at to solve quadratic equations. So the first method that we're going to use to solve quadratic equations is this thing called the square root method. Now, we can only use the square root method in specific situations. It's by far the easiest method, but unfortunately, like I said, you can only use it in specific situations. So you can only use it when you are in vertex form, that form we looked at in the previous slide, or when the independent variable x is only in one location. So I've got 3 quadratics down here. Which quadratics satisfy that definition? So is this one in vertex form? No, it's not. But is the independent variable x only in one location? Yeah, I don't see x anywhere else. It's only right here. So yes, that satisfies that definition. This I could use the square root method on. What about this next one here? Is this in vertex form? No, this is actually in standard form, ax squared plus bx plus c. Okay, but does it have the x only in one location? Unfortunately not. It has an x in the 8x squared term and has an x in the 2x term. So no, this does not satisfy that definition. I cannot use the square root method to solve that type of quadratic. Okay. Lastly here, y equals x minus 4 quantity squared plus 2. That is in vertex form. Remember, y equals a times x minus h squared plus k. That matches up beautifully with vertex form. That is the type of equation, yes, it satisfies the definition that I can use the square root method on to solve. So what we've got here is 2 different equations, quadratic equations. Why do I know they're quadratic equations? Because they both have an x squared piece to them. So 2 quadratic equations that I can solve using the square root method. This first one because x is only in one location. The second one because it's in vertex form. So let's take a look at this first one and how we would solve it. Now, square root method, there's only one unique thing about it. The rest is we solve it very similarly to the way we'd solve a linear equation. I'm first going to ask, is there anything I can add or subtract away from the x? There is this 36, so I'm going to add 36 to both sides to undo that. Let's see, 8 plus 36 is 44, so 44 equals 4x squared. Now I'm going to ask myself, is there anything I can multiply or divide away? Since my x squared is being multiplied by 4, I can divide the 4 away to undo that. So I divide both sides by 4. 44 over 4 is equal to 11, I believe. So 11 equals x squared. This is where it's a little bit different, and this is where the whole square root piece comes in. So I've got 11 equals x squared. I haven't quite solved for x yet because it doesn't say x equals something. It says x squared equals something. Question is, how do I undo a square? This is where that whole square root thing comes in. I undo a square by using a square root. But whatever I do to one side, I have to do to the other side. The square root and the square undo each other, and I'm only left with x. But here's the unique piece about the square root method. Anytime I undo a square with a square root like I just did here, the other side has to have a plus and minus sign put on it. So this other side is actually positive and negative square root of 11. So x is equal to the square root of 11, but x is also equal to the negative square root of 11. Question is, why do I have to do that? To illustrate that really quick, think about the square root of x equals 4. Actually, let's do it a little different. X squared equals 4. What values of x can I plug in here to satisfy this? Most people would see directly that you can do a 2, because 2 squared is 4. But what other value satisfies it? Not only 2 satisfies it, but negative 2 satisfies it, because a square undoes negatives. So you end up with negative 2 squared also equaling a positive 4. So we have to take into account both the positive and the negative versions. So that's why whenever we undo a square with a square root, the other side gets that plus and minus. So the solution to this quadratic is x is equal to positive square root of 11 and x is equal to negative square root of 11. And we're going to leave our solutions as exact. We could plug that into a calculator and get a decimal, but we're not going to. Let's look at the second example over here. We're going to do the same thing. Now, one thing that's very tempting to do is to take this 3 and distribute it in. I cannot do that because the parentheses have an exponent on it. The other tempting thing to do is to take this exponent and give it to each piece. I cannot do that either. I know that we're used to doing that, but this is not the same context. We did that when it was 4 times x squared. The squared belonged to each piece. The second you have a plus or minus sign between them, you can no longer do that. If I wanted to do x minus 4 squared, I would have to do x minus 4 times x minus 4. X minus 4 squared being the x minus 4 times itself. Working all that out takes a long time and is actually counterproductive to solving this equation. What I'm going to do is I'm just going to start peeling things away from the x, starting from the furthest pieces out and working my way in. So I'm going to ask, is there anything I can add or subtract? This 14 right here, I could add to both sides. 7 plus 14 is 21. So 21 equals 3 times x minus 4 squared. Now, is there anything I can multiply or divide away? Remember, I'm not going to distribute that 3 in because I can't, because it has an exponent on it. But what I can do is I can divide the 3 away. 21 divided by 3 is 7. So 7 equals x minus 4 squared. Now again, instead of having to do the x minus 4 times x minus 4 because it's squared, and also legally I'm not allowed to bring the squared into each piece because there's a plus or a minus between the values. It's only when everything is multiplied and divided together that you can do that. What I have to do at this point is undo the square. Because the whole x minus 4 is squared, I can square root the entire x minus 4. But whatever I do to one side, I have to do to the other side as well. But remember, whenever I undo a square with a square root, they go away, so it's x minus 4. But again, whenever I undo a square with a square root, the other side gets a plus and minus. Still not done solving for x. I still have a minus 4 on here, but now that it's no longer in the parentheses being squared, I can finally deal with it. I can add 4 to both sides. Now, don't be tempted to add 4 to 7 to get plus and minus the square root of 11. I cannot do that because the 7's under a square root and the 4 is not. I actually have to just take this 4 and put it in front of the plus and minus. Always put the plus and minus sign in the middle of the two values. So it's 4 plus and minus the square root of 7 is equal to x. 4 plus and minus the square root of 7 is equal to x. So the way I'm going to write this is x equals 4 plus the square root of 7, and x equals 4 minus the square root of 7. So those are my two values. Those are the two solutions, and I'm keeping them as exact. I could type in 4 plus the square root of 7 in my calculator, but I'm not going to. I'm simply going to leave them as exact solutions. So I want to look at two more examples, but the question we're going to ask is what happens when there is a negative under the square root? Fortunately, from a previous lesson, we know how to deal with negatives under square roots. They're called imaginary numbers. So let's see how those incorporate themselves into what we're about to do here. I can use the square root property because the x is only in one location here. So I'm going to start by subtracting 52 from both sides. Negative 2 minus 52 is negative 54 is equal to 6x squared. Okay, and I'm going to divide my 6 away. I believe that ends up giving me a negative 9. Negative 54 divided by 6 is negative 9. Check that in your calculator. And then I still have my x squared over here. But you can see now that I've got to undo my square with a square root. But whatever I do to one side, I have to do to the other side as well. So look what happens. A negative ends up under the square root. So the square and the square root undo each other. I'm left with x. But remember, whenever you have a square root undoing a square, the other side gets a plus and minus outside of it. So positive and negative square root of negative 9. Now, we have a negative under our square root. Thankfully, we know how to deal with that. Remember the quick trick? If you have a negative under a square root, simply pop an I out. So it's going to be plus and minus. The I goes directly in front of the square root. It doesn't go on the other side of the plus and minus. It goes directly in front of the square root. So positive and negative I root 9. And what is the square root of 9? It's 3. So this becomes positive and negative 3i is equal to x. So x equals 3i, that's the positive piece, and x equals negative 3i. So those are my two solutions. Notice that my solutions to this quadratic, they're not real, they are imaginary solutions. You're going to find that with quadratics that happens a lot. Why? Because solving quadratics involves square roots, and whenever you have a negative under a square root is when you have imaginary solutions. So let's do that one more time in this example over here. So remember, I can't distribute the negative 4, not going to do that. I can't distribute the exponent in, can't do that. So I'm just going to start peeling things away. I'm going to start by subtracting 40. 8 minus 40, I believe, is negative 32. So negative 32 is equal to 4 times x minus 3 squared. I'm now going to divide that 4 away. Negative 32 over 4, I believe, is negative 8. 8, 16, 24, 32. Yep. So negative 8 is equal to x minus 3 squared. And then square root piece comes in. To undo the square, I use a square root. But if I square root the one side, I have to square root the other side. Whenever I undo a square with a square root, they cancel each other out. I'm left with -3, or x minus 3. But remember, don't forget, whenever you undo a square with a square root, the other side gets a plus and minus sign. So positive and negative square root of -8. Now you're noticing that I've got a negative under a square root. I'm going to deal with that, but not yet. What I'm going to do first is, to finish solving for x, I need to add 3 to both sides. Now remember, this -8 is under the square root, so I cannot add 3 to it. The 3 goes in front of the plus and minus. So it's 3 plus and minus the square root of -8 is equal to x. Now I'm going to deal with the square root of -8. So because I have a negative under a square root, that quick trick is an I pops out. So it's 3 plus and minus I times the square root of 8 is equal to x. But does the square root of 8 simplify even more? 8 can be split up into 4 times 2. 4 can be split up into 2 times 2. I've got a pair of 2's with a 2 left over. So what comes out of the square root of 8? I have a pair of 2's, so a 2 comes out. So I end up with x equals 3 plus and minus, and I already came out. So a 2i is now what has come out, because the 2 out of here, times the square root of, I still have this lone 2 sitting underneath. So my solution then is x equals 3 plus 2i root 2, and x equals 3 minus 2i root 2. And again, because I ended up with a negative under the square root, I ended up with imaginary solutions, or in this case actually complex solutions, because they have a real part and the imaginary part.